story of a puzzle that drove scientists batty. This is a story set in the dark recesses of science. Our star is a creature of the night, an animal with skills that have defied explanation and inspired tales of horror. Its reputation has been blackened by rumors of evil and villainous pursuits. But for centuries, brave scientists have sought to conquer this mysterious creature, convinced it holds secrets that could change our world. Professor James Simmons is in his underground bat lab. At the cutting edge of biosonar research, Simmons has been collaborating for years with a colony of bat friends.
Okay, let me introduce to you Melanie. She eats insects. She flies around in the dark looking for moths and beetles. Melanie lives in a school here in Rhode Island when we caught her. She's part of a colony of about 20 bats. She chases insects for a living. Oh, there she goes. There she is. She can stay there while we do the interview. Lots of people are afraid of bats. They come out at night. People think bats are evil. They can find their way in the dark. Well, that's obviously a mystical process there, right there. They surely can't be natural if they can find their way around in the dark.
The super skills of these mysterious creatures have been frustrating scientists for centuries. Leonardo da Vinci was inspired yet defeated by the bat's unique way of flying. Fellow Italian Lazzaro Spallanzani was driven to distraction by bats' mystical vision. Today's scientists are just as obsessed by these winged wonders as their predecessors. They wish to understand how bats defy the laws of aeronautics, unravel the complexities of biosonar, and delve deeper into the galaxy of the bat brain. This quest has already spanned 400 years, kept alive by a succession of bat pioneers determined to decode this superstar of science. Count Buffon, a renowned 18th century French naturalist and predecessor of Charles Darwin, was horrified by such a misshapen being. Their uncertain and clumsy flight is obvious proof of imperfection, he wrote. He saw the bat as a freak of nature, a monstrous being. Buffon noted his observations in his 36-volume System of Nature, the Bible of natural history for years to come.
Buffon looked at bats and thought that they were bizarre. They're half mouse, half bird. Their faces are strange. They fly around in what looks like an erratic, almost incompetent way. You don't get to see the precision of the bat's flight and behavior with the naked eye at night. That's a crucial thing that Buffon was unable to notice.
Veritable speed merchants, these top guns of the animal kingdom can dodge trees whilst flying up to 80 kilometers per hour. They perform aerial acrobatics with perfect composure. Understanding their strange and very particular flight could help us to improve our own mastery of the air.
I think that an interceptor pilot would very much envy the ability of the bat to make sudden, very violent changes in course, and apparently to do it without effort.
I think the remarkable way that bats can move through space three-dimensionally, turning on a in an incredibly small distance and then turning again a fraction of a second later. I think that people who enjoy flying aircraft can't help but envy the ability of bats to maneuver through the sky in this complicated way.
Sharon Schwartz unravels the secret of animal biomechanics for the students of Brown University. The enigma of bat flight is her particular obsession.
To get a bat to fly really steadily in the center of a wind tunnel might take months of training. But I think the biggest problem is that many animals just don't adapt to the conditions of a wind tunnel. And so we often have to try 5 or 10 or 20 different bats before we find one that's really good at flying in a wind tunnel. This is the first time this bat has ever been in a wind tunnel. Doesn't quite know what to expect.
The continuous current of air coaxes the bat within the field of the cameras, which record between 500 and 2,000 images a second. Thanks to this device, Schwartz can observe her obliging subjects in minute detail.
Until we began to make high-speed films in the wind tunnel, we really had no idea of what the complexity of the wing shape was during flight. They're able to generate an incredible amount of lift at very low speeds, much more than birds. And there's clearly something remarkable about the wings that enables them to do that.
Schwartz's research could change the way we think about flying. Future flight technology may see the end of the rigid metal boxes we call aeroplanes, and the beginning of an entirely new, flexible craft.
One of the things about bat flight that lets them maneuver so violently is that a bat can maneuver its wings asymmetrically. A bird, when it flies, keeps the wings more or less symmetric. But when a bat flies, you can simply move one wing very differently than another and make a much more violent turn than a bird can in the same situation. It looks like it's erratic, but when you slow down, it looks more like they're dancing through the air. You can see the control in their movements, and you no longer get the idea that they're kind of flitting from one place to another without knowing what they're doing. So Buffon wasn't wrong about what he saw. He just didn't see it all.
It wasn't that Buffon was as blind as a bat. The strange morphology of these little creatures has inspired feelings of fear and suspicion for many centuries. In the Bible, bats appear alongside vultures and owls as unclean birds which must not be eaten. In the Middle Ages, the demons of hell, including Satan, adopted their winged membranes. Later, they would be associated with vampires and the living dead. All these superstitions clouded the views of the early scientists. But one Renaissance inventor and engineer did not fear the bat's shadowy reputation. At the end of the 15th century, Leonardo da Vinci started dreaming of a world in which men might fly. His study of birds is well documented, but less so the inspiration he drew from bats. Leonardo spent many a sleepless night trying to understand this animal, fascinated by its ability to lean on air. In his writings, he recommended to future students of flight, remember that your flying machine must imitate the bat. Its membranes are impermeable to air, and their movements regulate the wings. Dissect it and use it as a model for your machine. And centuries later, Sharon Schwartz is doing just that.
This bat has been preserved in formaldehyde and then in alcohol to allow us to carry out detailed anatomical study. Within the wing membrane, we can see a special set of muscles, little tiny threads of muscle that run along the skin that allow the bat to control the stiffness of wing membrane and control its shape in space because of controlling the stiffness. And then much of the wing is supported by the bones of the fingers. So these are really just like human fingers, only incredibly elongated. As we stretch the wing out, you can begin to see the forearm. Here's the elbow and the wrist, the fifth finger, the fourth, the third and the second together, and the thumb that extends off the leading edge of the wing.
If your hand was a bat wing, rather than sticking out about 10 centimeters like this, it would stick out about 3 or 4 meters like that on each side, and it would be tied to our legs and to the tail, which we would have to have.
Belonging to the Chiroptera order, meaning hand wing, the bat's wings conceal its hands.
This is a wing bone of a big brown bat. And by studies in which we've carefully weighed each element of the wing by using a very precise balance, we've been able to determine that the bones of the fingers of bats are far lighter than we'd expect for a mammal of their body size. This bone, for example, weighs only 0.008 of a gram.
This bearable lightness of being was a real obsession for Leonardo. How could he imitate such materials? How could he propel humans through the air? He dreamt up hundreds of designs, built several flying machines, but none of them would actually take off. Undeterred, Leonardo remained convinced that one day man would master the air. In one of his last notebooks, he wrote, "I have not been held back by miserliness or lack of will, only by time. Farewell." Four centuries later, Clément Ader, a wealthy pioneer of aviation, took Leonardo's advice and set about designing an extraordinary machine. After constructing many giant bat models based on the constant observation of these mammals, Ader found himself penniless. Fortunately, the French military, persuaded of the potential of such an invention, found the francs to allow the research to continue. In 1890, Ader finally took off in his bat-inspired craft and flew 165 feet at a height of 8 inches, before crashing back to Earth. After centuries of study and mimicry, the bat's unique aeronautical ability was still a mystery. A mystery that today's scientists continue to investigate.
We went into our studies expecting the wing to move almost like a paddle, and what we found is that there's folding going on everywhere along the wing of the bats. And not only are there movements at the joints, but the individual bones that make up the wings of bats are actually bending or deflecting during flight. Not a small amount, but an amount that's large enough for us to pick it up in video footage, to see a 10 or 15 or 20% change in the length of the bone as the bone bends during flight. You can't imagine bending a human bone this much.
Bats are the only mammals in the world to have such flexible bones. A lack of calcium and minerals helps maintain this elasticity. This revelation has propelled Schwartz's research into another dimension.
we've begun to take the information that we have about the position of the wings of bats in space during flight and put these into very sophisticated computer models that let us study what the flow of air around a complicated airfoil like a bat's wing. We can use a computer to model that and then use computer science approaches to visualize what these three-dimensional airflows are like. It's a little bit like being on the back of the bat and experiencing the flow of air around the bat as it flies.
Schwartz is working towards the day when this experience is more than a computer model, but may be encountered in a real live bat craft. Flying is a form of locomotion bats share with no other mammal. But this is not the only mysterious power bats have tucked under their wing. The perfect ease with which bats can travel at great speed, avoiding all obstacles in pitch blackness, is keeping yet another scientist awake at night. Professor Donald Griffin has been searching for answers for over 50 years.
So this is all brand new kind of research, which has never been done before, and I do not know how well it will work. Yes, for the moment.
And this evening, armed with a jam jar, some string, and a moth, he sets out to conduct his latest experiment on bat navigation. This 88-year-old bat wrangler's diligent research has opened the way for new generations of specialists, but he's yet to give up the chase. His accomplice, Greg Auger, a specialist in nocturnal photography, supervises the creative technical setup.
My dog's contribution to the cause. This is her bed. Now, as it gets a little wetter, it should start some more of that flow coming out from under it. The small bubbles in the water being caused by the rushing water give off a lot of high-frequency noise. And since the bats are utilizing high frequency for their navigation, and we're trying to study that, we want to cut down on as much of the noise as we can.
I am connecting this bat detector to Greg's camcorder so that it will record the time-expanded signals that we hope we will record from a bat. That is one way of getting the full range of frequencies, all the details that we can get out of the bat sound. July 27, 2003, very warm night. We're set up with our rig aimed out over the glade, and it was 82 at 7:32. And we hope the bats show up.
And so, the long wait begins. The first to investigate the mystical vision of these night creatures was an 18th century Italian naturalist. Abbot Lazzaro Spallanzani was not a typical man of the church. One of the founding fathers of experimental biology, he ignored biblical warnings against these unclean creatures and instead used exceptional rigor and determination to pursue only science and logic. It was in 1793 that Spallanzani's tormented obsession with bats began, when he first realized they could see in the dark.
If you suspect that bats don't use their eyes to find their way around, one obvious thing to do is to simply blindfold them, to cover their eyes and then let them fly around and see if they can still avoid bumping into things. And that was the first thing that Spallanzani did.
For 3 years, Spallanzani carefully documented his rigorous experiments.
I made a little bonnet of skin for one of my bats to see whether in the dark it would still know where to go. I carefully covered the whole of the animal's head without hurting it, released it, and it fell to the ground.
To be completely sure he was testing sight alone, Spallanzani used a process of elimination.
I pierced its eyes with little needles heated in the fire. With gouged out eyes, it flew perfectly, without crashing into the walls. My blinded bat could see.
I think that Spallanzani quickly realized he had an honest-to-God, genuine problem to solve.
I methodically looked for which other sense could help it to see in the dark. I blocked the nostrils of the blinded bat, then their mouths, and then their ears with glue. But none of the organs disabled in this way seemed to be linked to this mysterious blind vision.
If you look at a bat, he's very interested in the fact that a lot of the face and the wings of the bat is just naked skin without much fur. And one possibility is that the skin would contain touch, organs for the sense of touch, which the bat might use. So he covered the skin with what amounted to library paste to try to interrupt the ability of the bat to feel things through the skin. And under those conditions, the bats could still fly and avoid obstacles.
I tested hearing, smell, sight, touch, taste, and none of these senses, when eliminated, prevented them from seeing. Might they have a sixth sense?
He was trying to find out what the nature of this sense was, what organs were used to receive the stimuli that the animal used to find their way around. One of the things he found is that bats, when their mouths are covered up, are also helpless.
Thus began an infernal struggle. Spallanzani searched tirelessly to locate this improbable sixth sense. Hundreds of bats were sacrificed on the altar of his exhaustive research. He explored all facets of the animal, its resistance to cold, to heat, to light. He even examined the contents of its stomach. His hunger for knowledge knew no bounds. Failing to reach any conclusions, he embarked on a new series of experiments.
I burned the eyes of unused bats and subjected them to a new test, both in the light and in total darkness. They behaved as if they could see the threads perfectly well. They bent their wings to avoid them, and the bell stayed silent.
Spallanzani tried endless variations on the same theme. The bats continued to maneuver with exasperating ease. Perhaps they were creatures of Satan after all.
He probably thought something like this: how on earth am I going to explain this to people?
The bat conundrum was driving him to distraction. Exhausted, he finally asked for help. One of his correspondents, Swiss surgeon and naturalist Louis Jurin, was tasked to repeat his experiments. Jurin changed only one parameter. He used dense starch and not glue to seal the bat's ears. The results were astonishing. The bats refused to fly, they stayed on the ground, or crashed pathetically into the obstacles. The bats could not see.
He and the people he worked with and wrote letters to agonized about this. Do they see with their ears?
For the abbot to publish a conclusion which broke the rules of creation was unthinkable, a greater torture than being condemned to the flames of hell.
One of the hardest things in science is you have to be open to what you find. You can't say, wow, this is impossible. I don't believe this. You have to accept what you find, because what you see is the truth, no matter what it is. And the problem is trying to figure out how to interpret it. As Sherlock Holmes once said, when you eliminate the impossible, the only thing left, however implausible, must be the truth.
Without the words of Holmes to guide him, Spallanzani chose not to publish his work, refusing to believe the results. When the scientific community heard of Spallanzani and Jurin's experiment, they ruled the results erroneous due to the great suffering inflicted on the bats. The accepted theory of the day won through. The sixth sense was nothing to do with the ears, but linked to the sense of touch.
For a long time, this notion of tactile version of sensing things dominated thinking about bats, of which there wasn't very much, but it was sufficient to kind of bury Spallanzani's work for a century.
With Spallanzani's research collecting dust, the bats were able to escape further scrutiny. Returning happily to the shadows, bats were forgotten by man and by science. Out of the spotlight, they prospered in dark corners across the planet. Today, there are more than 1,000 different species. These bats have friends called tent-making bats, sword-nosed bats, and Asian false vampire bats. But interest in their mysterious abilities lay dormant until April 1912. As the unsinkable Titanic sank in glacial waters, Spallanzani's research resurfaced. American engineer Sir Hiram Maxim proposed fitting ships with a sixth sense, similar to the bat's blind vision. A sixth sense that could steer a ship around obstacles such as icebergs. Bat vision research was back on the agenda, but it took another 25 years for a breakthrough to come. In America. In 1937, our veteran specialist Donald Griffin was a young Harvard student, already passionate about bats, often frequenting dark caves carpeted in guano. He was to discover something which would radically change our perception of these small flying mammals.
When I first heard about Professor Pierce and his apparatus, I was quite timid about going and bothering this senior physics professor. I had not done very well in my physics courses, and I really didn't know much about sound. But my friends persuaded me that I really should do this, and I went with a cage full of bats and knocked on his door, and he was really quite interested. and took me to his apparatus, which had a microphone and the little device that translated high-frequency sounds into audible sounds, a loudspeaker. And holding the cage full of bats in front of this horn and microphone, we would hear from the loudspeaker of the apparatus a series of clicks, or sometimes continuous, almost clickety-click, click, click.
The noises which you will hear when I increase the gain are bat supersonic cries, converted by this device into audible sound.
It was clear that they were making a lot of high-frequency sound.
That day, 140 years after Spallanzani's failure, and for the first time in history, these two men heard a living creature emit ultrasounds.
We did not know why the bats were making sounds, and when animals make sounds, they often are communicating. So we considered that possibility. But we had the advantage that we had Pierce's apparatus, so we could tell when the bats were making these high-frequency sounds.
Donald Griffin and his friend Robert Galambos, a young neurophysiology student, repeated Spallanzani's experiments with the same rigor, but with no cruelty. Like their predecessor, they noted that with ears blocked, the bats crashed into obstacles. But with their detector, they also noted that with their mouths blocked, the bats could no longer emit ultrasound and crashed to the ground. With this new information, they deduced what those before them could not. Bats use sound to navigate the world.
In fact, what they're doing is a trick. The bat emits a sound and induces the object to make a sound to give away its presence. That sound is the echo.
Bats create an image of their surroundings through the number, intensity, and rapidity of the echoes they hear. Spallanzani's experiments did in fact hold the answer, but he had refused to acknowledge the impossible. Bats create an acoustic vision of the world with their very own sonar.
When the bat's using its sonar, it's more like this. It's close your eyes, open them, and close them again. Open, close, open. The bat gets this kind of stroboscopic picture of the environment only when it emits a sound. If a bat flies along making sounds 10 times a second, it's like it's blinking its eyes 10 times a second, and it's only getting images at that rate. This bat is looking at us with both vision and with sonar. The vision is showing the bright lights coming from outdoors through the windows, and the sonar is showing the details of all the objects in the room.
Griffin and Galambos gave their remarkable discovery the name echolocation.
It seemed incredible, even in 1940, that bats could be orienting themselves in the dark by making high-frequency sounds. It was such a new idea.
The discovery of echolocation in bats was widely disbelieved for a long time. A lot of people just couldn't imagine that the animals could do this.
When we reported this at a scientific meeting, one prominent physiologist was not at all convinced and took hold of Galambos by the shoulders and shook him and said, "You can't mean this."
They did indeed mean it, and Griffin continues to study the complexities of echolocation half a century on.
Greg, how does that look?
Let me check.
It's probably too low, but I can tighten the rope.
Yeah. I would push your time expansion start, Don, so we're ready.
Yeah, thank you.
I'm using a night scope, which is a military level image intensifier. And it is one of the pieces of technology that allows us to lift the veil of darkness at night. just cruising through.
I can hear them. I hear your bat detector.
Donald Griffin is exploring the idea that bats use their sonar for far more complex tasks than simple navigation. Tonight he is joining the bats on the hunt for food. Each evening he uses a different type of insect as bait. Tonight's dinner is moth.
I tried but could not succeed in getting bats to catch insects in the laboratory. They just didn't do it for me. On the other hand, the apparatus that we needed to detect bat sounds was quite expensive and elaborate. It needed AC power. It seemed rather ridiculous to take it out where bats were catching insects. So finally, with some trepidation, we did load all our apparatus in a small truck and took it out to a place where we had been watching bats catching insects. And suddenly things were very different. It was clear that they changed their sound in a very important way.
When a bat chases insects, it regulates the sounds that it emits, the rate it emits them according to the distance to the object. So when the object is far away, the bat goes chirp and then waits for the sound to come out and come back. After the echo comes back, the bat goes chirp. The sound goes out and comes back, but the bat's a little closer. So when this echo returns, the bat goes chirp, 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 chirp. And the rate of emission goes up faster. Towards the very end, when the bat goes like that, and you're listening to the sounds with the bat detector, it makes a buzzing noise.
And these clicks at 200 a second fuse into a sort of a buzz. And that has come to be called a feeding buzz when bats are feeding.
As it gets closer, the bat bombards its prey with ultrasounds, processing every movement, every detail, before going in for the kill.
Oh,
Hey, we got
that's a
one.
hit.
Did you get that last one?
Yes,
Good.
a wonderful hit. Nice buzz.
Yeah, we got it. We got the time expanded signals.
Okay, we're rolling. Oh,
It's a loud one.
nice and loud.
Good buzz. I'm still very much intrigued by how they use their sonar for very difficult operations, how they discriminate echoes from something they're interested in, like whether it is a good tasty insect or not, from all kinds of other echoes that they have to be getting. Here comes a bat.
He's still in there.
And we don't really know how their brains can do that, make that kind of discrimination. It's an intriguing mystery.
The speed at which this animal can process so much sound information is breathtaking. But how, in a cacophony of deafening echoes, does it differentiate one sound from another? How, for example, do female bats recognize their own young amongst a ceiling of thousands? It appears that bats have an individual ultrasonic signature, just as we all have a different voice. And it's possible that they use each other's signatures whilst flying to triangulate their position.
If you have several bats flying in a group, there is a possibility that when one bat emits a sound, it will produce echoes that some other bat can hear and use to see objects. So that you have multiple bats flying in a small area in a clearing in the forest, they can use each other's sounds, perhaps to illuminate the scene for each other. Do bats exhibit this kind of group behavior, which is called bistatic sonar, where the sender is in one place and the receiver is in another?
Our best sonars can't achieve anything like the rapidity of analysis of which a bat's brain is capable. The armed forces dream of one day having an equally efficient system to scan the underwater environment, to pinpoint mines which can destroy their expensive ships in an instant. For decades, the military have been trying to utilize these small, highly skilled creatures to their own ends. In response to the Japanese attack on Pearl Harbor, bats found themselves the newest recruits in the US Army. In 1942, a dental surgeon, Dr. Little S. Adams, wrote to the White House suggesting bat bombs could bring victory over Japan. President Roosevelt agreed and greenlit Operation X-Ray. Military tests started immediately. Able to carry more than their body weight, sleeping bats would be fitted with tiny incendiary bombs and released over Japan. On waking, the bats would take refuge under the wooden roofs of Japanese houses and trigger thousands of fires. But in tests, the bats didn't respond as intended. Some hit the ground still sleeping, others flew away, but the real problem recruits were those who returned their bombs to explode back at base. After spending an estimated $2 million and sacrificing thousands of animals, Operation X-Ray was cancelled. Dr. Adams maintained that his bat bombs would have been as effective as the atomic bomb dropped on Hiroshima. Donald Griffin had turned down an invitation to join Operation X-Ray, realizing its futility. Instead, he continued his own work on echolocation. Putting aside their strained relationship with bats, the military also refocused on animal sonar.
The Navy uses dolphins now, dolphins and other marine mammals, to find objects underwater, and they would very much like to be able to use remotely controlled vehicles with sonar to replace the animals. When man-made sonars are used, you use a different sonar to search for mines in a harbor than to find submarines in the deep ocean. Whereas a dolphin or a bat uses the same sonar to find objects, to chase fish or insects in the air, to fly through obstacles and things like this. And it's the fact that they use one sonar with great versatility that makes it especially technologically interesting. The plan is to try to understand how the bats do it, because it's easier to study bats than it is dolphins. At least some of the work can better be done using a bat as a surrogate for a dolphin.
Professor Simmons's work on animal sonar is in part financed by the US Navy. In his underground bat lab, his domesticated bats are helping him find out what goes on inside a bat's head.
This is a bat detector. It picks up the high-frequency sounds of the bat and converts them into sounds that we can hear, so that the sounds of the bat, which appear on the screen, sound like clicks on the soundtrack. When a bat is chewing insects when it's flying, it can't shut its sonar off, otherwise it might hit an obstacle, so it can make the sounds while it's chewing.
Their sonar can pick out objects finer than a human hair.
When bats determine the distance to objects from the delay of echoes, they appear able to detect changes in delay of fractions of a microsecond or fractions of a millionth of a second. All right? This seems impossible because neurons, nerve cells in the brain, seem to be able to measure time with accuracy only in the range of thousandths, not millionths of a second. So the question is, how do bats organize the interactions of cells in the brain to magnify their ability to make measurements of time with greater precision? What we hope to learn is exactly how the arithmetic in the bat's brain is organized, so that we could build a device that can process sounds and produce these images, this kind of sound motion picture, at the same speed as the bat. and also to make it relatively small and compact compared to most man-made systems. Looking at a bat brain, which is a very small thing right in front of you, you can hold it like this, it's just like a galaxy many, many light years away. You know something very interesting is happening there, but it's very frustrating because just like the galaxy, you can't always get at the thing that's happening and watch it while it works. The methods, even after 50 years of intensive research on the brain, the methods for observing what happens in the brain, particularly things that happen quickly, are still very primitive. It takes seconds to produce a brain scan image, but in a few seconds, a bat can catch 5 insects and then go hang up in a tree and go to sleep.
Exploration of the bat galaxy has only just begun, but could success bring a technological revolution? Will we one day have flexible flying crafts, machines that deftly dodge obstacles at high speed? Will the military realize their super sonar dream? Whilst we wait to find out, the stars of our dark kingdom will continue to fascinate and frustrate.
The conclusion of this night is that we've taken one more step in a long process. It may take 100 nights like this to learn anything at all. And we may decide after 100 nights that we have not learned anything at all. That's the way this kind of science works. But you take it as it comes.
What we're doing is we're continuing a scientific project that was begun a couple of 100 years ago by Spallanzani. And you have to combine appreciation of the importance of the people on whose shoulders you stand in science, so to speak, with Alfred North Whitehead's dictum, which is any science that hesitates to forget its founders is lost.
We have lost the bats for the night.
Well, that's the way it goes. The animals don't always do what you expect.
Okay, I'm going to shut the camera down.
Yes, I've turned off.
Next tonight, more scientists, different obsession. A fly's eye view of 100 years of genetic research. Superfly in just a moment.
Its story is the story of human cunning, of how navigators learned to travel by land and sea, of how artists learned to capture reality, of how we came to see the almost infinitely distant and the unimaginably small, of how we challenge the vision of a world created by God to enslave ourselves to a world that never stops. It is the giver of energy and the mother of revolution. It is light, and its story is the story of almost everything. Light Fantastic starts next Wednesday on BBC 4.